Good morning and welcome everyone to this course Physics 1. This course is generally made for undergraduate level BTech degree students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Paralpur. You can contact me personally at college premises, ground floor, physics lab. You can also send me your doubt, your question or your query regarding my video class lessons at given mail ID, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@jisgroup.org. I have a YouTube channel for my tutorial video for physics, so you can subscribe my YouTube channel for your regular class of BTech degree students, or you can also solve your query by learning from these online video tutorials. Now the corresponding course pages are www.markoutexam.net or www.markoutwb.ac.in. You can also find the syllabus of the physics subject for first year BTech degree students is uploaded there. The title of the course is Physics 1 and the subject code is BSPH 101. The category is under Basic Science course. The course has a credit 4 and 3 lectures per week and 1 tutorial per week. This course is generally made for first year BTech degree students. So according to the department, so odd semester some department will going to study this course, and for the event semester alternatively rest of the department is going to study this course. Today the topic will be covered are damped vibration, damping force, corresponding differential equation and solution for different case, logarithmic decrement, energy. So the corresponding prerequisites are fundamental of mathematics and elementary idea of simple harmonic motion. The course objectives are compare the observed motion of the system to a mathematical model of an object in damped vibration, to be able to mathematically model real-world mechanical vibrational problems. And after completion of this course, the course outcome, that means students will be able to measure the position and velocity as a function of time for damped vibration and determine the amplitude, period, phase constant of the object in damped harmonic motion. Also the energies involved in damped harmonic motion. They also able to identify or formulate and solve different type of engineering problems regarding this motion. So this topic also under the module 1 mechanics. So today I am going to discuss about the damped vibration or a particle executing damped harmonic motion. So before starting that damped harmonic motion, in my last video I have explained what is simple harmonic motion. So when I am explaining that simple harmonic motion, that is considering some ideal case, that means we have to neglect all the damping force, frictional force and other force, because considering this force the particle won't be able to execute simple harmonic motion. So now in a real life problem, which is basically common with the damped harmonic motion, I am going to discuss that. So that means when a particle executing simple harmonic motion with associated with some damping force or frictional force, then that simple harmonic motion now converted or considered as a damped harmonic motion, because due to the presence of that damping force or frictional force, its amplitude starts decay with time. So ultimately it will be stopped at infinite, the time will be at infinite. So basically in a real world or in a practical situation, almost every particle which executes simple harmonic motion, but it actually execute damped harmonic motion or damped vibration, because always there is a presence of damping force or frictional force. So that damping force or frictional force is actually resist the simple harmonic motion, so it will not possible for that particle to oscillate with a constant amplitude. So its amplitude will decay with time and it will gradually decrease and ultimately it will goes to zero. So this is the physical real world where the particle is executing damped harmonic motion or damped vibration. Now in my last day's video where I have discussed that simple harmonic motion, a restoring force comes into act. So here that damping force is oppose that restoring force, oppose the motion of simple harmonic motion or vibration for that particle, and ultimately it will be stopped by that application of that presence of damping force or frictional force. So this is the definition of damped vibration. So when the energy of a vibrating system is gradually dissipated by friction and other resistances, the vibrations are said to be damped. The vibrations gradually reduce or change in frequency or intensity or cease, and the system rests in its equilibrium position. So the examples are there. That means you may put a simple pendulum within some liquid. Okay, so due to that presence of the liquid, a frictional force, that means a resistive force, will act on that particle and ultimately it will going to stop. Say again, if you consider a mass spring system and if you put the mass within some liquid, so due to the friction of that mass with that liquid will act as a damping force or resistive force, and that particle will execute damped harmonic motion or damped vibration. Ultimately it will dissipate lots of energy due to that friction or presence of that resistive force, and ultimately it will be stopped. Now, in case of damped motion, damped vibration, that damping force is proportional to the instantaneous velocity of that particular object, always from mean position of rest. So, we can write F damping for Fd, that is proportional to minus of V, where V is the instantaneous velocity of the particle. Now we can write, so Fd is equals to minus of S into V, where S is the damping constant, damping force constant. So V can be replaced by dx dt. So we get Fd is equals to minus of S dx dt. So this is the expression of damping force or resistive force which actually resist or oppose the motion of particle which executes simple harmonic motion. So as we know, the simple harmonic motion can be written as m d2x dt2 plus kx is equals to 0. Now in the right hand side it will be not equals to 0, that will be opposed by that damping force Fd, which is equals to minus of s dx dt. So our process is almost similar as we have derived in my last video for simple harmonic motion. First we construct the differential equation of motion for damped vibration, then I will solve this equation for different cases putting the boundary condition, okay, to know the value of the displacement x of the particle executing damped vibration. As I have explained, we have substituted that value and we get m d2x dt2 plus kx equals to minus of s dx dt. Rearranging, we get m d2x dt2 plus s dx dt plus kx is equals to 0. Now dividing both sides by m, where m is the mass of the particle, we get d2x dt2 plus s by m dx dt plus k by m into x is equals to 0. Now we consider two constants. One is omega naught square, which is natural angular frequency of oscillation. So omega naught square equals to k by m and s by m equals to 2b, where s is a damping constant, m is the mass, that is also constant, so twice b is called damping factor. Substituting this value, we get equation 1, that is d2x dt2 plus 2b dx dt plus omega naught square x equals to 0. So this is the differential equation for damped vibration. Now we are going to solve this differential equation for damped vibration, which is d2x dt2 plus 2b dx dt plus omega naught square x equals to 0. So to solve this equation, I considered the solution is x equals to e to the power alpha t, where alpha is the constant. So it is a trial solution. So considering the value of x, that is x equals to e to the power alpha t, we can substitute the value of dx dt and d2x dt2. So dx dt is equals to alpha e to the power alpha t and d2x dt2 is equals to alpha square e to the power alpha t. Now if we substitute all these value in equation 1, we can take e to the power alpha t common. So as e to the power alpha t is not equals to 0, as it is already a solution of x, so we get alpha square plus 2b alpha plus omega naught square equals to 0. Now according to Sridharacharya, we can write the solution of this equation is alpha equals to minus b plus minus root over b square minus omega naught square. That means it has two solutions and two values of alpha. So one is alpha 1, that equals to minus of b plus root over b square minus omega naught square, and another one is alpha 2 minus b minus of root over b square minus omega naught square. So we get two different constant value, one is alpha 1, one is alpha 2. So our complete solution is x equals to a e to the power alpha 1t plus b e to the power alpha 2t. So alpha 1 and alpha 2 value is already calculated, but here the constant a and b are unknown. So to get the ultimate or total solution of x, we have to substitute the value of a and b, which is an unknown constant. So how we will solve this constant or solve this equation? To know the value of a and b, we have to put the boundary condition for different cases. So simplifying this equation, we get e to the power minus bt common and we substitute by value of alpha 1 and alpha 2, we get x equals to e to the power minus bt within bracket a e to the power plus under root b square minus omega naught square plus b e to the power minus under root b square minus omega naught square. Now for the simplicity, we consider another constant n value is equals to under root b square minus omega naught square. So ultimately we get the solution of this differential equation 1 will be x equals to e to the power minus bt within bracket a e to the power plus nt plus b e to the power minus of nt. And the velocity of that particle executing simple harmonic motion v equals to dx dt, which gives us minus b e to the power minus bt within bracket a e to the power plus nt plus b e to the power minus nt plus n e to the power minus bt into a e to the power plus nt minus b e to the power minus nt, which is equation 3. So we have derived the simplest form of expression of displacement x in equation 2 and the simplest form of the velocity of that particle in equation 3. Now the damped harmonic motions has 3 different cases. First one is overdamping, second one is underdamping, and last one is critical damping. So overdamping is the case where b square is greater than omega naught square. This is the condition for overdamping. That means the damping factor value that must be greater than that natural angular frequency of oscillation. Now if we consider this graph that is shown in the right hand upper side, the displacement of the particle with time, you can see at starting point, that means at 0 time, it is already executing simple harmonic motion before application of damping force. So it has a initial position and initial velocity. So at t equals to 0, it has x equals to x naught and v equals to v naught. At t tends to infinity, that means after application of that damping force, resistive force or frictional force, its amplitude tends to 0, so corresponding velocity will be also 0. So our first boundary condition is t equal to 0, x equals to x naught and v equals to v naught. So substituting this value in equation 1 and equation 2. Here not in equation 1, as per my video you can check, it is equation 2 and equation 3. So the expression of displacement and expression of velocity. So if you put at t equals to 0 in equation 2, you get x naught equals to a plus b, and if you substitute t equals to 0, v equals to v naught in equation 3, you will get your v equals to minus of b into a plus b plus n into a minus b. So you got two equations, one is for x and another is for v. So solving, and your objective is to find out the unknown constant value a and b, as two unknown constant is there and you have already two equation is there. So solving these two equation, you can easily find out the value of a and b. I have solved this differential equation, and after getting the value of x, we solve that value to find out our velocity expression, then put our boundary condition t equals to 0, x equals to x naught and v equals to v naught. So we get x naught equals to a plus b and v naught equals to minus b into a plus b plus n into a minus b. From there we can calculate by solving these two equations to know the value of unknown constant of a and b. So after knowing the value a and b, you can substitute all these value in your expression of equation 2 So that will give you the total ultimate solution of x, that means displacement, for overdamping case. Second one, it's a critical damping. So critical damping is the case where your damping factor will be equals to the natural angular frequency of oscillation. So your B will be equals to omega naught. So substituting that value in equation 1, that will give you the differential equation for damp vibration under critical damping case will be d2x dt2 plus 2 omega naught square dx dt plus omega naught square x is equals to 0. So considering in similar way, considering the value of x equals to e to the power alpha d, we can solve this differential equation to get the value of that alpha, that is equals to minus omega naught. So it has only single value, and the corresponding solution of this equation is x equals to a plus bt whole into e to the power minus omega naught t. So equation 5 is the solution of this differential equation. Now again putting the same boundary condition as t equal to 0, x equals to x naught or v equal to v naught, we can get the value of a, unknown constant term, a equals to x naught and b equals to v naught plus omega naught x naught. So substitute all this value in equation 5, you get x equals to e to the power minus omega naught t within bracket x naught plus v naught plus omega naught x naught whole into t. So this is the ultimate solution of x, that means displacement for a particle executing critical damping. Now the last one, that is underdamping. So underdamping means your damping factor B that will be less than omega naught. That means your natural frequency, natural angular frequency of oscillation will be greater than the damping factor. So rearranging, we can write under root b square minus omega naught square, that is equals to under root minus common omega naught square minus v square. So as we know, the root over minus 1, that is the complex value, that is denoted by I. So this equals to I omega. So you can write the value of the solution x equals to e to the power minus vt a to the power I omega t plus b to the power minus of I omega t. So now elaborating this e to the power I omega t, that means as we know omega t is theta, so e to the power I theta is formula is cos theta plus I sin theta or cos theta minus I sin theta. So here we substitute that value, we get x equals to e to the power minus bt a cos omega t plus ia sin omega t plus b cos omega t minus ib sin omega t. So you can substitute all these value, and considering a plus b equals to m cos theta and I into a minus b equals to m sin theta. So substituting this value, we get our ultimate solution of x, that is equals to m, where m is a constant, so m equals to e to the power minus bt cos of omega t minus of theta. So we get by putting again the same boundary condition as I have discussed earlier, that at t equals to 0, x equals to x naught and v equals to v naught. So we get m value is under root x naught square plus within bracket v naught plus bx naught by omega square and whole square. So after getting the value of m, so that means all the solutions are complete. So we can write the solution of x is, that is equals to under root x naught square plus v naught plus bx whole square by omega square e to the power minus bt cos of omega t minus theta. So this is the ultimate solution of damped harmonic motion when it is under damping. Now the next topic, that is logarithmic decrement. So what is logarithmic decrement? It is basically logarithmic decrement represents the rate at which the amplitude of a free damped vibration decrease. So it is defined as the natural logarithm of the ratio of any two successive amplitudes. So it is used to find the damping ratio of an underdamped system in time domain. Now, in case of damped oscillation, logarithmic decrement measures the rate of decrease of amplitude. So, the displacement of damped oscillation at any time t can be written as a naught e to the power minus gamma t by 2 sine square omega t. So, sine of omega t. So, here we can write a of t, that is equals to a naught e to the power gamma t by 2, where a naught is the amplitude of undamped oscillation and t equals to 2 pi by omega, it is the time period of oscillation. Now the displacement is 0 at t equals to 0 and t by 2 and 2t by 2, where capital T is the phase or time period, basically here time period. So t equals to 0, t equals to t capital T by 2 or t equals to 2t by 2. If you substitute this value and we get the corresponding value of the amplitude or displacement, and that will be maximum at small t equals to t by 4, 3t by 4, 5t by 4 onwards. So if you substitute all these value, we get a1 equals to a naught e to the power minus gamma t by 2. Again we get t, the displacement will be maximum at small t, that means time will be when equals to capital T by 4, 3t by 4 and 5t by 4. So if we substitute that value, we get a1, the amplitude at time capital T by 4 is equals to a naught e to the power minus gamma capital T by 8. A2 is equals to a naught e to the power minus 3 gamma capital T by 8. A3 equals to a naught e to the power minus 5 gamma T by 8, and so on. So if we take the ratio of a1 by a2 or a2 by a3 equals to an minus 1 by an, that will give us e to the power gamma t by 4. Thus the ratio of two successive amplitude of the damped oscillator is always a constant, and that value can be taken as equals to d, that is the decrement of motion. Hence the logarithmic decrement will be denoted by lambda. So lambda equals to ln d. So ln e to the power gamma capital T by 4. So that value gives us that logarithmic decrement is denoted lambda is equals to gamma capital T by 4 or gamma by 2 into capital T by 2. Hence the logarithmic decrement is the natural logarithm of the ratio of successive amplitude separated by a time small t equals to capital T by 2. So that is equals to half of the time period. Now a1 by a2, that will be taken as equals to e to the power lambda. So a1 by a3 can be written as equals to a1 by a2 into a2 by a3, that is equals to d squared. So that is equals to e to the power 2 lambda, that is equals to e to the power 3 minus 1 into lambda. So it can be written as a1 by an, that will be equals to e to the power n minus 1 into lambda. So where lambda is equals to 1 by n minus 1 ln a1 by an. So determining the value of a1 an and noting the value of n, we can easily determine our logarithmic decrement value, which is lambda. Now the time constant. So time constant is the time required to decrease the amplitude 1 by e times of its initial value. So you have to find out what is the expression of that time constant. So time constant is the smallest, or it is the time required for which its value will decrease 1 by e times of its initial value. So here it is given as 1 by e, that is equals to a naught e to the power minus of gamma into t plus r whole divided by 2 by a naught e to the power minus gamma by 2. So that gives us 1 by e equals to e to the power minus gamma r by 2. So e to the power minus 1 is equals to e to the power minus gamma r by 2. So equating the power of e, we get r is equals to 2 by gamma. So r equals to 2q by omega naught. So q equals to omega naught by gamma. So here r is also called the relaxation time or modulus of decay. So it can be represented as tau, or it can be represented as, here I consider it is small r. So it is the time constant for which its amplitude decay 1 by e times of its initial value. Here it is an application where you can consider the damping. You can calculate the damping in case of an LCS circuit. So for an LCS circuit, you can know as per application of KVL, so you can calculate all the voltage drop across the capacitance or across the inductance or across the resistance R, that will be equals to 0. So we can write Q by C, which is the voltage drop across the capacitance, that is equals to minus of L di dt, which is the voltage drop across inductance, and minus of Ri, which is the voltage drop across resistance. So equating these two, we can form a differential equation which is almost equal or equivalent to our differential equation of damped vibration. So comparing these two, you can easily calculate what are the damping factor, what are the damping constant, or the corresponding related terms. So all I have derived here, you can check. So this is an important application where you can compare with all the coefficient. You can easily find out the damping constant, damping factor, or damping force as per our formula that I have already discussed. So these are the books that I have referred. You can consider it as your reference book. Evaluation process is same: internal exam for 30 marks and external exam for 70 marks. Hope all of you have understand this damped vibration. In next class, I will discuss the force vibration. Thank you.